Okay, let's begin with a sound check. Can you people in the back row hear me all right? Can you back there hear me all right? Great. As you can tell, my voice is not in the greatest condition, so the microphone will have to do most of the work for us. Before I continue with our discussions of Chapter 2 and water, are there any questions that people have left from Chapter 1 and the course syllabus, the course organization, so forth? Okay. We do have handouts for Chapter 2 here if you didn't bring yours with you or you don't happen to have it. Angie, would you be willing to deliver some if people need them? Does anybody still need a handout for Chapter 2? If you could help out with that. While she's just doing that, I'll announce her study group tonight. Angie will be happy to meet with people who would like to discuss the material so far or discuss strategies for learning biochemistry, anything to do with that. Raise your hand if you need Chapter 2, please. It'll be tonight at 5:30. It'll be in room 433 Bowen Science Building. It's voluntary, but the students who took advantage of help like this last year enjoyed it and found it very helpful. In general, we will hand out the handouts for chapter the day we begin it. And I will usually hope that you'll bring it with you thereafter so we don't have to kill more trees. But we will bring whatever remaining copies there are with us, either here or over there. So it's there if you need it. And if you don't happen to get it here, there are always copies on file at the main biochemistry office. Thanks very much, Angie. All right. So let's go to aqueous chemistry. Let's get started to talk a bit about water and why it is such an amazing solvent and such an amazing compound. The fact that it has the capacity to make up to four hydrogen bonds at once makes it unusually capable of making extensive networks, as you're seeing here, of hydrogen bonds. In water, those hydrogen bonds are very short-lived, but they can occupy at least 3 and sometimes 4 of the potential hydrogen bonding sites. As a consequence, water tends to hold together. If you were to have a molecule of methane there with all the hydrogens on its surface, it's like having a box full of BBs. They just roll around over each other. Whereas with the water molecules, it's like they all have a little bit of Velcro on them. Some have Vel and some have Cro, and they get tangled. And so it gives it a really remarkable set of properties. Because water is so polar, and because it can make 4 hydrogen bonds, up to 4 hydrogen bonds, it has an unusually high surface tension. That is, the organization of the water molecules at an air-water interface is unusually tightly knit together, so much so that, as you can see here, there are insects that will walk across using nothing but the surface tension to keep them up. It has a high melting point. It might not seem high to us. It's on the ground outside right now. But if you were to compare it to something like methane, you'd see it's much, much higher than that. It has a high boiling point. These 2 numbers are the bracket that determine life. Since we need liquid water, it's only going to exist between those 2 numbers. Because there are so many hydrogen bonds between the different molecules, it takes a lot of heat to make them move faster. And that's the shorthand way of saying it has a high heat capacity. A high heat capacity means that living things have a thermal buffer around them so they don't change temperature as easily as if they were made out of something like methane. The hydrogen bonding capacities make it a good solvent, and we're going to discuss that in a little more detail. It's one of the best solvents that there is. And I think I mentioned before that the extremely tight packing, or detailed, extensive packing of ice makes it less dense than water, and then the oceans don't freeze up. And so that's, for us at least, a good thing. I think it's handy to keep in mind the relative strength of different kinds of bonds. This is a graph that's trying to convey the sort of scale of interaction that we're talking about. So if the covalent bond is taken as this strength, units here happen to be kilojoules per mole, an ionic interaction between a fully plus and a fully minus charged thing is less than a quarter of that, maybe 20% of that, but still clearly some interaction there. And we're going to see places in biological molecules where ionic interactions are very important. Hydrogen bonds are maybe 20% of that. So now we're getting really a small fraction of a covalent bond. But because there are so many hydrogen bonds in living systems and in aqueous systems, they end up being extremely important. And then finally, we'll talk about what a van der Waals interaction is in a little bit. It's obviously a very, very weak force indeed. But sometimes if you have a lot of something very weak, it adds up. And that's what's being conveyed by this picture. I don't know how many of you are familiar with the book Gulliver's Travels, but at one point Gulliver gets nailed down to the ground by the little people that he's visiting, and feels very ashamed that such little people can capture him and hold him prisoner. And it's a metaphor for the fact that even though the hydrogen bonds are weak, many of them together will add up to being enough to make a difference structurally. This is giving you a sense of length, which is a correlate of strength. The shorter the bond, the stronger the bond, and this gives you a sense of what it is. If you're that distance apart, those two atoms are not bonding in effect. And you can see how the hydrogen bond is intermediate between the two of them. Some of the places where we see these kinds of interactions are in things like the DNA molecules, where the hydrogen bonding is extremely important for the ability to make base pairs. And so you can see again oxygens and hydrogens interacting to make hydrogen bonds, or an hydrogen and a nitrogen here. We also see what are called van der Waals forces, where weaker partial charges can orient atoms against each other. This is an oxygen to a carbon, not to a hydrogen. So this is a partial negative charge again, but here it's the carbon, not a hydrogen. Another force for interaction are called the London dispersion forces. In this case, the molecules undergo a certain amount of random fluctuations, and if one of them fluctuates to the point where this hydrogen happens to get a little bit of a positive charge, it can induce a negative charge on the hydrogen across from it, which will then propagate along. Those are very weak forces, but they in fact add up to, again, being one of the things that make molecules hold together. So why is water such a good solvent, and how does that operate at the cellular level? Well, it is capable of solvating or hydrating, adding water molecules in a loose but extensive association with molecules in one of two ways. If the compounds are ionic, they'll interact with it, or if the compounds are polar. And so between those two groups, water can solvate an awful large fraction of the world. Sorry. Here's just an example of water solvating an alcohol with a hydrogen bond. Here's one with an amine group. If we think about the cell, the interior of the cell, up to 50% of that volume is occupied by proteins and other solids. So this is a drawing that tries to capture that sense of crowdedness. And if you think of it in this scale, which is more true to life than the usual diagrams that are easy to look at but misrepresent the density of it, what it adds up to is that each of these larger molecules has a little layer of a few water molecules, one to a few, that kind of hover around its surface, keeping it in solution. And one way of thinking about these hydrating water molecules is they are kind of a bumper that actually keeps molecules from just simply aggregating completely. If you put the same kinds of molecules that would be dissolved in water in a cell into a nonpolar solvent, they'll almost always precipitate out. And so the water is helping to keep those things free where they can interact. This is just simply showing you in a diagrammatic way how that kind of solvating works. So here you have actual ionic compounds. And these shells of water, these are sometimes called hydration shells, those are an important part of the effective size of an ion. So you will not see a sodium ion that has no water around it. So the effective size of a water ion, of a sodium ion, is really sodium plus its waters. And the same way for the chloride ion. Here the hydrogens are pointing their partial charge towards it. And again, the effective size has to include the water molecules because they won't come off spontaneously. Here you can see a glucose molecule. Clearly with all of these alcohol groups, each of those alcohol groups will also be a polar group, just like the OH of the water molecule is. So each one of those alcohol groups is a wonderful candidate for hydrogen bonds that help to solvate it. Well, that's great for things that are ionic or polar. And we've talked about how you can recognize polar molecules through the electronegativity series. But what if you're not polar? What happens then? Then we get to talking about something called the hydrophobic effect. And hydrophobic literally means fearing water. Now, most molecules have a very limited psychological interior life, so this is just a metaphor. The comparison term for a polar molecule would be hydrophilic, loving water. And in general, a non-polar compound will be hydrophobic. Here's just an example of an extremely dull one. This is dodecane, so it's 10 carbons with all the spare bonds filled in with hydrogens. You can see there's not much room in there for much polarity. You can get a little bit of those London dispersion forces going, but it's not going to be very interesting. And because of that, because this can't make hydrogen bonds to any significant extent, water molecules cannot take up any orientation at all relative to it. They have to sort of balance out so that they're not pointing one end more to the other then. And so the understanding we currently have for how the hydrophobic effect works is that it's due to a loss of entropy. So if you think for a moment of putting a nonpolar molecule into this flask, like the dodecane, the water in immediate contact, immediate vicinity, immediate neighborhood of the molecule is not as free to move as the water out in the bulk solvent. And so there's a loss of entropy. This water is less disorderly than the water elsewhere. Now, in nature, things don't like to have a decrease in entropy, as you know if you've looked underneath your bed. And so, at least underneath my daughter's bed. Sorry, I didn't mean to do that. Back, here we go. Back to the slideshow. Sorry. So what happens is if you add into the solution multiple nonpolar molecules, I hope this isn't going to do something terrible here, then each one of those molecules, which you can sort of see there, each one of those hydrophobic molecules will have a constrained layer around each one of them. And I'll just do body language now until this decides to make up its mind. So each one of those has its own constrained layer. And if all of those together just collide and are in a neighborhood with each other, then there is going to be a constrained layer of water around the droplet, as you can see over here. So these are more orderly. The nonpolar molecules are more orderly because of the hydrophobic effect, but it's favored because the water overall is less orderly. So that's what drives the hydrophobic effect. It's not that nonpolar compounds have any particular attraction to each other. They don't, except for London dispersion forces and things like that. But they're, you can imagine if you were at a high school prom and nobody talks to you, you might end up talking with the other kids who nobody talks to. And that's basically what's going on here. And that'll stay in your minds, right? So that's what the basis of the hydrophobic effect is, that the water becomes more disorderly by the nonpolar things hanging out together. And because of that, the hydrophobic effect can drive the formation of various kinds of structures. The one we're going to be talking about in considerable detail right away is about membrane structures, and we'll talk more about that when we talk about membranes. But hydrophobic effect is also extremely important for protein structure, and we'll be talking about that as well. Hydrophobic effect plays some contribution to nucleic acid structure, but there's an additional interaction there called stacking interactions that we'll talk about when we get there that are not, strictly speaking, hydrophobic effect, so just to be aware of that. I'll mention it again when we get there closer. Any questions about that before we plunge ahead? Hydrophobic effect is a little weird. A lot of people take a while to absorb it, even if you've seen it before. Okay. Well, suppose you had a compound that was hydrocarbon at one end and then a carboxylic acid at the other. So this part is extremely nonpolar. It's just like our dodecane molecule. And this end has this carboxylic acid with its two oxygens and its negative charges and stuff. So this end is polar. And we would call such a molecule amphiphilic, loving both. It loves both water polar molecules and nonpolar hydrophobic molecules. And you can remember amphiphilic because it's like amphibian. Amphibians live on land and water. So amphibians both. And when you think about that, then you're going to wonder, well, if that's what the structure of it looks like, what does it do when it's put into a compound? And what happens in water then is that the tails, the hydrophobic tails, will they will tend to sort out of water. That is, each time they come together, there'll be less, more entropy outside of them, so they'll tend to stay there. And the polar heads will continue to interact with water the way any polar group would. Now we can get a number of different patterns if we use amphiphilic compounds with different composition. So over here we're looking at a compound that has a polar head group and two nonpolar tails. And here we have a polar head group and one nonpolar tail. If you take enough of this kind of compound and mix it together and look in the correct ways, you can find it making a bilayer like this. Where all of the hydrophobic tails are found sequestered away and the head groups are all oriented towards the water. In the molecule with a single tail, it will again sort out from the water, but it'll take on an appearance like this, where it's like a droplet, a teeny, teeny, tiny droplet called a micelle. And again, the hydrophobic tails tend to sort away and the heads go that way, but you don't get the layer, you get the droplet. And the difference in geometry here is because of the geometry of the molecules themselves. In the case of this molecule, the heads are functionally speaking larger than the tails, and this is the only packing that gives the heads enough room. Whereas in this case, the tails are taking up a fair bit of space, and this geometry allows the maximum number of them to be out of contact with the water. These lipid bilayers have some truly, truly wonderful behaviors. Because they have some polar and some nonpolar characteristics, they can control what's inside the structure. And so here what we have is a lipid vesicle. It has a double layer of lipid here. So all the red parts are their polar heads, and the green is the oily interior. And if you think about this, you'll see that anything that is polar is going to have a hard time getting through that. So salts, proteins, most metabolites, because they are associated with water, they're hydrated, they have that hydration sphere around them. For them to get through the lipid bilayer, they'd have to have all that water stripped off. And so it's an unlikely event to happen. For the things that do go through, they can follow mass action. So things that are capable of moving through that will go through in proportion to their concentration. Do you think that nitrogen would go through a membrane well? Any thoughts?
Yes.
Great. Why would you say? Could you explain your answer?
It's a fairly small molecule. It's not polar, so it's pretty easily.
Great. So it is small and it's nonpolar because it's a homodimer. There's nothing there to be different about it. What about oxygen? Same logic. So it's pretty free to move through too. The gases can move, these gases can move through freely. What about water? How quickly do you think water moves through membranes? For something like this, it'll go through more slowly. So if it's just a lipid vesicle, water goes through slowly. If you look at the membrane of real cells, the water goes through fairly well. And it turns out there are pores that allow the water to go through. In the absence of those pores, the water would tend to stay on whichever side it is to begin with. What this means is that cells can make an interior environment that is constant and different from the exterior. And if you look at the interior of cells, it turns out that most cells have fairly similar compositions, not universally, but a surprisingly large variety. If you look at the extracellular fluid in our bodies, in us as we're alive, it turns out that the composition of the extracellular fluid is extremely close to the ocean. So it's a lot of sodium and a lot of chloride and a little bit of some other things, even to the extent that the concentration is not that different from the ocean. On the other hand, if you look inside the cell, it's a clearly non-random population. This is so different from that it has to be maintained actively by the cell. The other thing that's funny about this is there's a lot of potassium, there's not much chloride. And if you think about electrical balance, you'd have to wonder why we aren't all just little capacitors wandering around full of charge. And the answer is there's a lot of negative charges on proteins, on nucleic acids, and so on. And those are the counter ions that balance the potassium. It goes both ways. So we've talked about water as if it stays the same, but it doesn't quite. And the fact that it doesn't quite stay the same opens up the whole range of acid-base chemistry in aqueous systems. There are acids and bases in non-aqueous systems, and I'm not capable of giving you an intelligent discussion of those. But the ones in aqueous systems are extremely important to life, so we're going to spend a little time thinking about them. One water molecule can dissociate into one negatively charged hydroxide ion and one positively charged proton. Although the proton is not found free in the cell, it's found to the extent that you can talk about it as what's called hydronium. For shorthand, we'll talk about it as a proton, but in reality, it's got a water molecule making love to it. And what we see if we look at the structure of water in detail through the kinds of methods that have this resolution is that these protons go moving around. So if we have here a hydronium with one extra proton, if it jumps to here, that will bump on one off to there, and so forth. So the protons can just hop from one water molecule to another, sort of like in billiards when one ball pushes the other one off to the next direction. So water can dissociate, but it does not do so very much. Like any molecule, you can talk about a constant for the undissociated and the dissociated products. This is what the standard definition for such constants is, the two dissociated products and the original thing there. Now in water and for water, the concentration of water is essentially constant. It's not going to change significantly compared to the ions. So we treat it as if it's constant, and we can talk about the Kw. And the product of the concentrations of protons and hydroxide ions is 10 to the minus 14th. Very small number. And when you have equal amounts of hydrogens and oxygen, hydroxide radicals, you have 10 to the minus 7th molar hydrogen protons and 10 to the minus 7th molar hydroxide ions. That's 1 in 10 billion, right? I think so. 10 million. 1 in 10 million. Now the product has to stay constant. You see, this is a K for a constant. So the product of these two things has to be always 10 to the minus 14th. And what that means is that in the solution, if there are things that are generating more hydroxide ions, there will be fewer protons free in solution. If you have something that's releasing protons into the solution, there'll be fewer hydroxide ions in solution. It's only at neutrality, right there, that you have equal concentrations of both. So we would call a solution like that a neutral solution. 10 to the minus 14th is a huge range to try to talk about in any practical way. It's really much too big to do on an everyday basis. And so chemists a long time ago came up with the pH scale. And the pH scale is simply using the fact that these are logarithms. So you have 10 to the minus 1, minus 2, and so forth. So you can use the logarithm of the concentration of the protons. And we're going to use the negative logarithm because these are negative numbers to begin with, and it gives us a positive scale. All right? A little bit convoluted, but it ends up giving us a scale basically from 1 to 14. At a neutral solution, you have 10 to the minus 7th molar protons, 10 to the minus molar hydroxide ions. That would be pH 7, equal amounts of both. So if you have a pH lower than 7, that's comparable to saying 10 to the minus 4th protons. The two together have to be a total of minus 14, so you don't have very many hydroxide ions then. Similarly, if you're going up in here, you're going to have more hydroxide ions than protons. So anything below pH 7 is acid, anything above it is basic. And so we can talk about the pH of a solution. And if you add acid, that will usually lower the pH. Adding base will raise it. Here we're using a definition of acid as a proton donor and a base as a proton acceptor. So typically, for instance, if you put hydrochloric acid into water, you're going to end up with protons, protonated waters, hydroniums, and chloride. So this would increase the concentration of that, lowering the pH. Here, when you add the sodium hydroxide to water, you'll have a free sodium ion, and this isn't quite balancing. I'm sorry, there's an error in there. 2OH. I'm second. All right. Right. And we can take advantage of the fact that there are a number of molecules that only dissociate a bit. And we call these things weak acids. That is, if you were to go back there, if you put hydrochloric acid into water, essentially all of it dissociates into hydrogen ions and chloride. For a lot of biological molecules, only some of it will dissociate. And so we call them weak acids or weak bases. And to take as an example, here's acetic acid. Acetic acid is a weak acid. When it's put into water, it will form some protons and acetate ions, and some of it will remain in the form of acetic acid. And so we can talk about its dissociation constant. You can have the association products up there, the original acetic acid down here, and water. But again, the concentration of water is not going to change significantly, so we talk about the dissociation constant, and here we have the dissociated products over the starting material. So this is a way to measure the tendency of a molecule to dissociate. Now, the tendency of weak acids and weak bases to dissociate also exhibits a very large spectrum of behavior, and so we can tame that range the same way we did for protons. And the pK measurement is related the same way that pH was. So pKa would be the negative logarithm of the association constant. And that allows us now to work in a range from roughly 0 to 14. So in the case of acetic acid, the pKa is 4.7. So it's telling us that some will associate. You'll have a bit of protons in there, but not as much as hydrochloric acid of the same concentration. It's a little bit unintuitive in that the larger the pKa, the less it's going to dissociate. The smaller the pKa, the stronger an acid. So it's a little bit backwards in that respect. I don't expect you to memorize these, but this is to give you a sense of some of that scale of pKa's and the tendencies of groups that you're going to see often to dissociate or not dissociate. Hydrofluoric acid is stronger than many biological acids. Here's the acetic acid we just talked about. Bases, this is a compound that gets used as a buffer. Look how close it is to neutrality. We're going to see why that's a good thing in a little bit. Here's imidazole, another buffer that's often used, and the basic building block of some other molecules we're going to see later on. Here's ammonium ion, and it has a rather high pKa, so it tends to be basic, it makes solutions basic. And that's part of the reason why ammonia in general is something that biological systems have to deal with, and we're going to talk about that in nitrogen metabolism. So when a weak acid or a weak base dissociates, it will change the concentration of the solution. I'm going to talk a little bit of math here. I'm not going to ask you on the test to solve numerical problems. I would prefer, I will be happy if everybody has a qualitative sense of what's going on here. But I do want to go through the math so you get a chance to see it. So this is what's happening at the chemical level. The weak acid can dissociate into the conjugate base of the proton. We've talked about the Ka already. We can rearrange this equation so that the Ka is now over here and the proton concentration is over there. If we then convert those to negative logs, this proton concentration turns into pH, and the pKa, the Ka turns into pKa, and we end up with this rearrangement of the equation overall. So this is an equation called the Hasselbalch-Henderson equation that allows us to relate the intrinsic tendency of a molecule to dissociate and the actual concentrations of its components to the pH of the solution. So this is a very valuable way of trying to predict or to understand what effect weak acids and bases, and many biological molecules are weak acids or bases, what influence they'll have on the solution. Something that makes some folks a little uncomfortable with pH, ionization, and so forth, is that the effects of ionization will depend on the group. And I'm going to focus here on two of the groups because they are two very common ones that are going to occur again and again, so you need to feel comfy with them. So here's a carboxylic acid. And if you were to look at it in a pH -2 or a pH 2 or lower solution, that solution has a lot of protons available. It will be in the protonated form here. If you were to look in a more intermediate range, between say 4 and 9, there's a lower concentration of protons. It's now in a deprotonated form. It's lost its proton because there are not so many around. It is now ionized. If you continue to raise the pH with, I don't know, say hydroxide or whatever, still proton poor, it remains deprotonated and ionized. By contrast, if you have an amine group, in the conditions where it's proton poor, it is unionized and in sort of the basal state, if you like. As you drop the pH, there are more protons in the solution. As the pH gets lower and lower, it will become protonated and ionized. And of course, the lower the pH goes, it can't pick up any more. That's where it is. So these two groups, the carboxylic acid and the amine, which are very common groups, have this sort of contrast in what the effects of protonation is. When you protonate a carboxylic acid, it's now neutral. When you protonate an amine group, it's now charged. And it depends just on the chemistry of it. But that's why we call this a weak base and this a weak acid. Okay? Any questions about that before we go on? Okay. So we've talked about the fact that the interior of the cell has to be in a particular range. And there are some things out there in the world that can change things rapidly, change the pH rapidly. So for instance, hydrochloric acid, since it completely dissociates into ions, will produce a large change in pH. There'll be a lot of new protons in that solution. It will be a more acid solution. Now, an interesting fact is that if you have hydrochloric acid and a bit of a conjugate base around, okay, so this is the acetate ion. when those protons dissociate, some of them will be taken up by the acetate to become acetic acid and a neutral form. And so if you have weak acids and bases around, they can act as what we call buffers. They can reduce the amount of change in pH you get by adding a strong acid or base. And let's look at that graphically here. So this is what's called a titration curve, where you can add more and more base to raise the pH higher and higher, or you can start at the high pH and add acid to bring it down. It'll happen the same whichever direction you do it in, okay? And if you wanted to start with a solution in which all of the acetate is protonated, say fairly acid here, and you start adding base to it to remove protons from it, the pH of the solution will start to rise. But then for a while, it rises less than you'd expect for the amount of base you're putting in. It's acting as a buffer. It's changing the rate of change in the pH. It's tending to oppose the change in the pH. And you notice that this is curving down, that's curving up. We call something like that an inflection point. It's also the midpoint. And at that concentration, you have equal amounts of the protonated and unprotonated forms. You have half of the acetic acid, half of the acetate, half and half. As you continue to add base, again, there'll be a slower rise in pH, but at some point it has to overcome the tendency to buffer, and then we end up at whatever the final concentration you want to work with. So if we just take this particular one of acetate, the protonated forms will be always down where the pH is greatest, but for acetate that will be the unionized form. As we strip protons away by raising the pH, we'll end up here. It'll be all ionized. It'll be all deprotonated. And the midpoint is half protonated, deprotonated, half ionized, half unionized. This midpoint is the pKa. It's a very convenient property of the way we've set up the system that the midpoint in that titration curve is equal to the pKa. And you can use that in either direction. In other words, you can use a titration curve to tell you what the pKa is, or if you know the pKa, you can say at that pH, half of them will be protonated and half will be unprotonated. And below it, more will be protonated, and above it, fewer will be protonated, and so on. Are people comfy with that? Any questions? I know it seems kind of obvious, but it's important to have a good grasp of this because we're going to come back to things that ionize and deionize a lot. One place where weak acids play an extremely important role is in the human blood. This is something that those of you who have some medical interests, and I know there are more than a few of you, will find of great interest later on, because the ability of bicarbonate in the blood to control pH turns out to be a key physiological property of humans. Now, if you have carbonic acid here, and this is bicarbonate, those two are in some equilibrium, so that if carbonate is protonated, it becomes carbonic acid, and carbonic acid in its turn can turn into water and CO2. Now, the tendency of carbonic acid and to go to those two things is not all that great, but there's an enzyme called carbonic anhydrase that catalyzes that, and so that's a reaction that can be facilitated. If you have some situation that is generating extra protons, so for instance, maybe you've been running anaerobically and there's extra protons floating around, those can associate with the bicarbonate in the blood, generating higher concentration of carbonic acid, and through the law of mass action, it'll tend to dissociate and be released as carbon dioxide, facilitated by carbonic anhydrase. If you have a condition where the pH of the blood is higher than it ought to be, if you're in it's what's called alkalosis, then as you breathe in carbon dioxide, the carbonic anhydrase can make carbonic acid for you, which then can dissociate and make available protons that then can lower the pH in response to that stress. So the bicarbonate happens to be at a pKa that allows it to serve as sort of a safety feature in either direction. And it's partly so good because we keep producing carbon dioxide all the time, and because we can equilibrate it against the atmosphere. There are also buffering things done with phosphate in the blood, but it's much harder to get rid of phosphate quickly. So the short-term control is principally through bicarbonate. So I think what remains for the rest of these, this handout is going through some of the specifics on these molecules and making sure that you have sort of fluency with what's doing what. So for instance, would this be a hydrogen donor or an acceptor? Hydrogen bond donor or acceptor? Acceptor, right. And how about here? What would be likely to happen there? Is nitrogen different in electronegativity from hydrogen? Mm-hmm. So this hydrogen will be partially positive, and that'll be partially negative. So this one could be a donor of a hydrogen bond. And you can take a peek at some of the rest of those molecules again. This is taking a look at a number of compounds and asking you to think through whether these things will tend to form intermolecular bonds or not, all right? And would you guess that this would be very prone to forming bonds between, let's say, the pure solution of it, would it tend to make intermolecular bonds? If you had a flask, a vial that was just this compound in it, would it tend to make intermolecular bonds between the different molecules? In other words, would one of them tend to make a bond of any kind to the one next to it? And if so, what kind of bond? Mm-hmm. So in other words, this one will have that partial negative charge that's very common in a carbonyl oxygen. That's probably going to have a bit of a partial positive because that oxygen's withdrawing some of that electrons, right? How about this molecule? Thoughts? Will this be a polar region? Where would there be polarity in this part, if any? So right, so the hydroxyl group is polar, where this is going to have some partial negative, and that will have some partial positive. And so you're going to have kind of an awkward association there, but it could have some. It would do it two at a time, though, right? It can't make more than one hydrogen bond in each direction. So unlike water, which can make 4 hydrogen bonds at once, since each of these can only make 2, they're not going to do nearly so well at it as water would do. Yeah, let's see now. Let's take a look at figure 234. Take a look at these molecules and look at them for a bit and see if you can put those compounds into a series from most soluble to least soluble. Take a moment. You can talk to each other if you want while you do this. Okay? From most soluble to least soluble in water specifically. Okay? And you're certainly free to talk. care to offer? Which one would be most water soluble? Great. You're seeing the strong carbonyl oxygen there in the two amine groups. Next most water soluble after C? D? You've got the carbonyl and that again, but this is now a methyl. Next. And that would be because of a carbonyl but no nitrogen rather. Next one. So it has an ether there, which will be a little bit polar, but it's not as strongly so as some of the other arrangements you see oxygen in. And what would be the least water soluble? Right. So you can look at molecules and make sense out of them. You can look at them and know something about how they're going to behave. Take a look at these and as it says on it, which of these are polar, nonpolar, or amphiphilic? And for the ones that are amphiphilic, would they make micelles or bilayers? Okay? Take a look at them and see if you can decide. People feel I have a sense of this yet? Are there any compounds in here that are polar? So, a little louder. A is polar, okay. So this is the part up here that would be polar. Is there any part of that molecule that's nonpolar? Okay. So if it's got some polar and some nonpolar, then it's an amphiphilic compound, right? So this one's amphiphilic. Polar, nonpolar, or amphiphilic? Nonpolar, right? Just hydrocarbon, straight hydrocarbon. Polar, nonpolar, or amphiphilic? Polar. This is a quaternary amine ion. Yeah. Kind of a funny ion, but that's what it is. Here? Polar, right. That methyl group isn't enough to call it amphiphilic. So that gives us two here that are amphiphilic. For the two that are amphiphilic, I guess I jumped the gun by saying that's amphiphilic, but hey, if you got the first one, you got that one. So what would these form, micelles or bilayers? Micelle or bilayer? Micelle or bilayer? So again, the structure of these things does tell you things about what's going on. Okay. This is 237. Is this one polar, nonpolar, amphiphilic? Amphiphilic. Anybody recognize the name of this? Sodium dodecyl sulfate. Take a look tonight at your toothpaste or your shampoo. If they're not too expensive, they'll say sodium dodecyl sulfate. If they're expensive, they'll call it sodium lauryl sulfate. Sodium lauryl sulfate is chemically identical to sodium dodecyl sulfate, so there's no real reason to pay more for it. But this is an extremely common detergent, and because it has a sulfate at one end, it's a strong detergent. It will tend to dissociate structures like dirt in your hair very effectively. Okay. Which of these molecules, this is 238, which of these would cross a bilayer spontaneously? Okay, want to argue that for me? Want to explain your answer, I really mean. Honest man. I love honesty. It'll tend to diffuse through because it's small. It's a polar compound. If you think about oxygen and carbon, those bonds are polar. It's a linear one, I think. If people can correct my chemistry in this, but it's small, so it slithers. How about calcium? Sorry? Yeah, right. Calcium is usually associated with pumps and channels because it won't go through spontaneously well. That is a full charge on it. It's not just polar, it's charged, and it's got the huge hydration shell around it. It will not go through spontaneously. What about glucose? Okay, want to offer an explanation? So it's bigger than the carbon dioxide. They're both polar, but this is a lot bigger. And so it, again, needs channels or pumps to go through. How about this molecule? It's a little weird looking. Since we're kind of close on time, I'll pop you the answer. This part of it is non-polar, so it tends to favor going through. These groups are somewhat polar, but as long as they're uncharged, it's tolerated. So this molecule can diffuse through in the unionized form. But this group or this group can get protonated or unprotonated and drop or gain a proton. And so this thing can carry protons across a membrane by picking up a proton on one side and losing it on the other. So it will tend to destroy a difference in pH between one side and the other. See you on Wednesday.